Hi, everyone. Good afternoon. I think we should go ahead and get started. It's a great pleasure for me to introduce today's colloquium speaker, Mike Manfra. Mike got his PhD from Boston University, and then he spent a decade at Bell Labs, and since 2009, he's been a professor at Purdue, where he also runs a fruitful collaboration with Microsoft. Mike is a world leader in the study of ultra-high quality, low-dimensional electron systems. In recent years, he's done a lot of beautiful work on the quantum Hall effect and engineered topological superconductors, motivated in part by the pursuit of intrinsically resilient quantum information hardware. Today's talk is going to focus on a really groundbreaking experiment from Mike's group, where they've achieved what many consider to be the first direct and definitive observation of quantum statistics beyond the usual bosons and fermions. I think this is a spectacularly exciting advance. Mike has agreed to take questions during the talk, so if you have any questions, feel free to use the raise your hand function or enter questions in the chat box, and I'll be monitoring that throughout this today's colloquium. So with that, Mike, thank you so much for being here today, and please go ahead and get started whenever you're ready.
Okay, thank you, Jason, and thank you for inviting me to give this presentation. So I'm going to tell you about, start my video, yep. And tell you about our attempts to observe anyonic braiding statistics in quantum Hall systems. And I just want to mention that these experiments were done by a fantastic graduate student, James Nakamura. The samples were grown in my laboratory by Shuang Liang and Jeff Gardner. Okay, let me go forward here. Okay, so the topics I want to try to cover, this is a colloquium, so I'm going to try to give an introduction to the quantum Hall effect, at least a very basic one. So if people aren't familiar, they have at least an idea of the language I'm using and what the system is we're considering. I'm then going to move on to the Aharonov Bohm effect and braiding statistics in electronic versions of the Fabry-Perot interferometer. I'll tell you about the challenges of operating electronic Fabry-Perot interferometers in the quantum Hall regime, and a new heterostructure design that we've come up that has helped mitigate some of these challenges. We'll then move on to operation of the interferometer and the integer regime at nu equals 1, and in the fractional regime at nu equals 1/3. And finally, I'll tell you about the data that seems to suggest we're actually seeing anyonic braiding statistics at nu equals 1/3. So the quantum Hall effect occurs when a two-dimensional electron gas is subjected to a quantizing magnetic field at low temperatures. But there can be a variety of forms that this two-dimensional electron gas takes. And I was talking to a lot of the graduate students earlier, and many of them are working on graphene, which is truly a two-dimensional system, or atomic sheet of carbon atoms. I wanted to give you a little bit of an introduction to the system we're considering, the two-dimensional electron gas, or more appropriately, the quasi-two-dimensional electron gas that resides at the interface of semiconductor heterostructures. And so, as I said, the quantum Hall effect occurs when we take a two-dimensional plane of electrons and subject it to a quantizing magnetic field. Now, in the system we're considering, gallium arsenide, aluminum gallium arsenide heterostructures, this two-dimensional electron gas resides at the interface between a narrow bandgap semiconductor, gallium arsenide in this case, and a wide bandgap semiconductor, aluminum gallium arsenide. And we intentionally put silicon impurities that have an electron, a valence electron that they can donate to the system that gets trapped at the potential step that's at the aluminum gallium arsenide interface. And so the 2-deg resides at the transition from the blue region in the center panel from gallium arsenide to the aluminum gallium arsenide, which is in green. And if we look on the right-hand side, we show what the conduction band profile looks like as a function of position. That's shown in red. And the larger band gap material, the aluminum gallium arsenide, is butted up against the gallium arsenide, and there's a potential step right at that interface. As you see, we also plot the electron density as a function of position. And so there's the electron density is not actually a delta function. There's some spread to the density of over on the order of a few tens of nanometers. And so this is what we mean by when we say we have a quasi two-dimensional electron gas confined at the interface between these semiconductors with different band gaps. Okay, so I also want to tell you how we actually make these in case you're not familiar. This is quite different from graphene. We grow these structures in a system called a molecular beam epitaxy system. It's an ultra high vacuum system where we pump out all the residual gases to a background pressure of about 10 to the minus 12 torr, about 15 orders of magnitude lower than the surrounding environment. Gallium, aluminum, and arsenic are provided by heated sources that produce beams of atoms for epitaxial growth. And we can achieve by moderating the conditions in the MBE chamber, achieve atomic layer precision with this extremely low disorder. And this is, of course, necessary to achieve the fragile correlated states that we're examining in the fractional quantum Hall regime. And on the right-hand side, I just show you a TEM image of a multiple quantum well stack. The bright areas in the picture are gallium arsenide, the darker regions are aluminum gallium arsenide. And because of the precise lattice matching between the aluminum gallium arsenide and the gallium arsenide, we can grow these layers and stack them on top of each other basically at will. We can grow hundreds of narrow quantum wells and barriers without generating defects because of the really nice lattice matching between the two semiconductors. And so this is the technique we use to fabricate the two-dimensional electron gases that we'll be talking about in our experiments. So I want to give you the simplest introduction to the quantum Hall effect. This is not by no means meant to be in-depth or exhaustive. It's just to set the stage and establish the language that we'll be using later on. So if we take a two-dimensional electron gas and subject it to a perpendicular magnetic field, we can consider what terms are in our Hamiltonian. Of course, there's going to be the kinetic energy associated with particles moving in 2 dimensions in a perpendicular magnetic field. There will always be some residual disorder, and disorder is actually important in the quantum Hall regime. It is what localizes quasiparticles and gives finite width to the Hall plateau. And of course, there's the residual interactions between the electrons in the plane, the mutual Coulomb interactions between the electrons. Now, Coulomb interactions aren't necessarily, it's at the simplest level to describe the integer quantum Hall effect, but they're absolutely vital to the description of the fractional quantum Hall effect, as we'll see shortly. But let's just consider the case, the simplest case, where we neglect the disorder potential in electron-electron interactions and consider the problem of non-interacting electrons in the two-dimensional plane. And of course, this Hamiltonian is nice in that it can be solved exactly. We all solved it in our introductory quantum mechanics classes. And we can write down the eigenfunctions and eigenenergies of these states, but semi-classically, we also know what happens if we put electrons in a magnetic field. They'll start undergoing cyclotron motion. The cyclotron frequency is given by EB over MC. E is the electronic charge, B is the applied magnetic field, M is the band mass, C is the speed of light. Now, if we solve this Hamiltonian exactly, we can write down the eigenstates, and depending on gauge we choose, they'll be specified by 2 quantum numbers, N, an orbital quantum number, and in this particular case, K, which is associated with the wave vector of the particular state we're looking at. Now, interestingly, the eigenenergies take on a very simple form. It's just h bar omega c times n plus 1/2, where n is this orbital index called the Landau level index, after Lev Landau, who solved this problem back in the, shortly after the advent of quantum mechanics. But what's interesting, while the eigenstates are labeled by 2 indices, the eigenenergies are completely specified once we give the Landau level index n. So what this implies, of course, is that there can be a large positional degeneracy associated with these eigenenergies. Many eigenstates share a common eigenenergy. And this positional degeneracy plays an important role in the quantum Hall effect. The positional degeneracy scales linearly with the applied magnetic field. It's area times B divided by phi naught, where phi naught is a magnetic flux quantum. And if we look at the density of states, we'll form these series of discrete Landau levels that are separated by the cyclotron gap, h bar omega c. Now, before moving on, I want to define a parameter called nu, which I'll use throughout this talk. It's called the filling factor. Basically, the filling factor is given by the number of electrons times the magnetic flux quantum divided by the flux through the active region of the device. More succinctly, it's the density of electrons times phi naught divided by b. And it tells us the number of Landau levels that are filled with electrons. It's called the filling factor. So if we look at the density of states as we apply this large magnetic field, the spectrum becomes singular. We have these well-separated orbital Landau levels, and we consider what happens as we fill up these states. So imagine that we have exactly one electron for every available state on the lowest Landau level. That would be filling factor nu equals 1. We have one Landau level filled. And in this case, the Fermi level would reside in the gap between the lowest Landau level and the n equals 1 Landau level. And this is the region that we'll associate with the integer quantum Hall effect. The Fermi level's in the gap between the Landau levels, and we can expect to see some transport features, as we'll get to in a second, associated with that. Of course, it could also be true that we have the density of electrons is such that we have 2 Landau levels filled, and that would be filling factor nu equals 2. There's no reason that we have to have an integral number of Landau levels filled. We could have a partially filled Landau level, and this case would be different. We'd have the Fermi level residing in the Landau level, and we'd expect the state to be compressible as we have available states at the Fermi level. So, but let's consider the case where we have an integral number of Landau levels filled, say 1 or 2. And let's consider what happens to transport in that regime if we measure transport. Well, as I said, we have a completely filled Landau level, say we're at nu equals 1. The bulk is insulating. The Fermi level's in the gap in the interior of the sample, so the bulk carries no current. And if we measure current, that this current actually flows through chiral edge modes that propagate along the edge of the sample, schematically represented by these skipping orbitals I've shown you in red at the edge of the sample. And what's interesting, if we measure the longitudinal resistance along one of these edges, we'll get, in the integer quantum Hall regime, we'll get 0 resistance. We'll have no backscattering. And this is a property of the edge states in the quantum Hall regime, that they're topologically protected. In order to cause backscattering, a electron moving in a right-moving edge state at the bottom of the sample would have to scatter into the leftward propagating edge mode at the top of the sample. And since they're physically separated, this is greatly suppressed, and therefore we see 0 resistance along the length of the sample. Concomitantly, if we look at the voltage that develops transverse to the flow of current, we find that each filled Landau level contributes 1 quantum of conductance. So the conductance is nu, the filling factor, times the fundamental quantum of conductance E squared over H. So typically we're measuring the Hall voltage, not the conductance. And so we find that the Hall resistance is quantized to 1 over nu times H over E squared, where nu here is again the number of filled Landau levels. We're assuming here that we have an integral number of filled Landau levels. So this is what gives rise to the unique properties, transport properties in the quantum Hall regime, the integer quantum Hall regime. But this, of course, only applies when we have an integer number of filled Landau levels, and we're considering a non-interacting picture of the electron motion. So we, of course, could continue to increase the magnetic field till we have the fractional filling of the lowest Landau level, shown schematically at the bottom. Here we would expect a huge degeneracy. The Fermi level would be in the Landau level, many states available, and our naive expectation would be that we'd have a compressible state. There's states we don't have to add energy to add particles to the lowest Landau level. Of course, this is a simplification brought about by our assumption that we're dealing with non-interacting particles, and we only have to consider the kinetic energy term in our Hamiltonian. What we've completely neglected here is the strong electron-electron interactions of the electrons in the lowest Landau level. In fact, when we are in the lowest Landau level and there's a large gap to the next orbital Landau level, all the electrons share the same kinetic energy, and we can basically take this out of the problem. It could be the new zero of energy. And so really what defines the physics in the lowest Landau level is the residual interactions between the electrons. And so we can see this is non-perturbative. There's no small parameter here. The kinetic energy is essentially quenched by having a large magnetic field. And so these strong electron-electron interactions give rise to incompressible states at certain rational fractional fillings, 1/3, 1/5, 2/3, 2/5, for example. And so actually we see incompressible fractional quantum Hall states, and this is completely due to the strong interactions in the system. So we're going to be working primarily in the fractional quantum Hall regime, and there are consequences of these strong interactions are that the excitations of the system, the gap is driven by Coulomb interactions, that the excitations of the system have very unusual properties. So the excitations of the fractional quantum Hall effect are emergent quasiparticles. And on the right-hand side here, I just show you transport through a pretty standard sample these days in gallium arsenide. It's fairly low density, it's about 1 × 10⁻11. So in the regime below, say 4.5 Tesla, this is the area where we are studying the integer quantum Hall effect. There's fractional states in the n=1 Landau level, but primarily we're looking at the integer quantum Hall states. And as we get to higher magnetic field, we're in the lowest Landau level, and there we're probing the fractional quantum Hall states. And the phenomenology, the quantization of the Hall resistance and the zero of longitudinal resistance is qualitatively the same in the integer and fractional regimes, but the gaps actually have much different origins. In the integer regime, it's a gap in a single particle density of states, while in the fractional regime, is driven by the gap is driven by strong electron interactions. And we're going to be focused primarily in this talk on the primary Laughlin state at μ=1/3, up around 12 Tesla here, and that's going to be the one that we'll examine in our interferometry studies. But to continue on, the quasiparticles of the fractional states have many unusual properties. Primary among these is that they carry fractional charge. At the μ=1/3 state, the charge is E/1/3, 1/3 of the bare electron charge. And this was demonstrated experimentally over 20 years ago in shot noise experiments, that the charge is actually fractionalized in the fractional quantum Hall regime. Now, another equally interesting property that the quasiparticles in the fractional regime possess is that they are believed to have fractional braiding statistics. And what that means is that they don't behave as normal bosons or fermions, which would have a phase of 2 pi or pi under exchange, respectively, between the bosons and the fermions, but they have some intermediate value of exchange statistics, or braiding statistics more correctly. Theta anion is given by, for the Laughlin states, 2 pi E*/E. Basically, the filling is given by the filling factor and the ratio of the effective charge to the bare charge. And so what do I mean by that? We have a statistical angle that is 2 pi/3 for the case of the Laughlin state at μ=1/3. Well, what this means is you can envision taking a quasiparticle, one quasiparticle, and dragging around the other in a process we call a braid, that the system develops a quantum mechanical phase 2 pi E*/E. And of course, this implies at μ=1/3 that the theta anion is 2 pi/3. This was originally shown by Halperin and Rovas and collaborators back in the mid-80s. Now, while this is theoretically well established that there should be fractional braiding statistics, it's been experimentally difficult to demonstrate for a number of reasons I'll go into shortly. So while the fractional charge is well established, the fractional braiding statistics has only recently come under scrutiny and been able to be seen in experiments. Now, we're interested in examining phase in the fractional quantum Hall regime. And if we're interested in phase, One way of examining phase in general, of course, is interferometry. Interferometry experiments are exquisitely sensitive to phase differences that can be accumulated both in optics and in the electronic version that I'm going to describe to you now. And so what we're actually examining is an electronic analog of a Fabry-Perot interferometer. We're going to be looking at it in the quantum Hall regime, first the integer quantum Hall regime, and then the fractional quantum Hall regime. So what I show you here on the left is a cartoon of what the Fabry-Perot interferometer looks like. The blue region is meant to represent the two-dimensional electron gas, and the yellow regions are surface gates that we put on top of the two-dimensional electron gas in order to define the interference path. In the analog of the beam splitters, that electronic beam splitters are these quantum plane contacts, these two narrow constrictions at the left and right-hand side of the interferometer. And we use these quantum plane contacts to partition the current that flows in the sample. So as we just got done describing, in the quantum Hall regime, the current is carried by chiral edge modes. This chiral edge mode comes into the first quantum plane contact, and we partition the current here. Some of the current is backscattered, the edge on the other side. Most of the current is actually transmitted through the interferometer until it gets to the second in QPC, where again, some of the current is partitioned off and circulates back around the interferometer, while most of it continues on to the drain current, drain contact. Now, of course, the current that circulates around the interferometer develops a phase as it circulates around relative to the current that was backscattered at the first QPC. And this phase difference that develops will, of course, modulate the conductance that we see developing across the device. So if things are working in accord with our naive expectations, in the integer quantum Hall regime, this phase that develops, or phase difference, can be written out in the following form. The backscattered current will have a the constant terms that are proportional to the reflection coefficient squared at the amplitude of the reflection coefficient squared at each QPC. But then there'll be an oscillatory term that comes about from basically the cross product of the interference terms, and that will oscillate as a cosine function, where the angle that develops, if everything is working properly, is nothing but the Aharonov-Bohm phase. The Aharonov-Bohm phase is given by 2 pi AB over phi naught. A is the area of the interferometer, believed to be controlled in the simplest terms by the gate voltage we apply to the side gates, and is modulated by the magnetic field that we apply that pierces the interferometer. So we can measure the interference by measuring electrical conductance across the device. We can operate the device by either changing the area by the gate voltage on the side gate, or by changing the magnetic field. Now, if we make plots of conductance in the BG plane, the BVG plane, we expect lines of constant phase to have negative slope. And this was demonstrated theoretically by Halpern and co-workers back in 2011. So this is colloquially referred to as a pajama plot, or barbershop holes, where the lines of constant phase have negative slope. And if you see lines of negative slope, that's indicative that you're actually operating in the Aharonov-Bohm regime. Now, if we move from the integer quantum Hall regime to the fractional quantum Hall regime, this phase gets modified in two important ways. First, the AB contribution is scaled by the effective charge, so of the quasiparticles that are circulating around in the edge states. And so the period of the AB oscillations would no longer be phi naught, but it would be, in the case of the nu equals 1/3 state, 3 phi naught. But equally interesting is the fact that the phase is now sensitive to the presence of localized quasiparticles within the bulk of the interferometer. So the phase has a contribution that is the number of localized quasiparticles inside the interferometer times this anyonic phase. So in principle, by measuring the interference pattern that develops in the fractional regime, we should be able to extract information about this anyonic phase. So if you can imagine, what would be ideally seen is these lines of constant phase under Aharonov-Bohm evolution. But then when a quasiparticle is introduced into the system in the bulk of the interferometer, that there be phase slips associated with this, since the quasiparticle number can only change discretely, can change by 1 or 2, that there be basically glitches in this Aharonov-Bohm oscillation of the conductance associated with the appearance of localized quasiparticles. And so we face AB evolution and then phase slips. And that's actually what we're going to be looking for in our experiments. Now, this seems simple enough, and it seems like, wow, this should be something you can do readily. What I'm going to tell you now is what's presented challenges for doing this type of interferometry in the quantum Hall regime and the solutions that we've come up with to mitigate some of these challenges. So if we actually start looking at interference in quantum Hall interferometers, we'll see that the behavior is quite different. And the problem is that in my simple description so far, I've neglected Coulomb charging effects. Now, I've described this as an inert interferometer, but of course, these are mesoscopic devices. They're small, and they're not that dissimilar to actually quantum dots. And if we actually start measuring the interference in one of these devices, what you'll often see predominantly is lines of constant phase having positive slope, just the opposite of what I told you. And again, this observation in real devices can be attributed to our neglect of the strong Coulomb charging effects associated with small objects, small mesoscopic objects. So if you actually consider what's going on, the Coulomb charging effects cause the area to change with magnetic field. The area of the device is not independent of magnetic field. As I increase the magnetic field, I actually change the area. It's a question of energetics. The flux actually decreases as I increase the magnetic field. So I cannot make changes to A and B independently when Coulomb coupling is considered. It's again a question of that there's finite charging energy associated with these small devices. They're much like quantum dots, and there's an energy cost to be paid to putting charge onto the device. The system compensates by changing its area to minimize this Coulomb charging effect. Now, importantly for us in our discussion, again, for devices operating in this what's called the Coulomb-dominated regime, there is theory that shows, again, by Halpern and co-workers, that you should indeed see lines of constant phase with positive slope. And this is the indication that you are working in this Coulomb, where Coulomb physics is actually dominating the interference. Now, importantly for our discussion, I won't go into the details, but operation in the Coulomb-dominated regime precludes the observation of anyonic statistics in principle. Basically, any change in phase that comes about for the introduction of a quasiparticle is compensated for by a change in the area of the device such that the overall phase changes by an unobservable multiple of 2 pi. So this is a real problem for observation of fractional statistics. So what we have to do is somehow quench these strong Coulomb effects that necessarily come in when you're looking at small devices. So I want to give you a little bit of a background and that leads up to how we solve this problem in this dichotomy between seeing AB oscillations and CD or Coulomb-dominated oscillations. And we got some very good hints from previous experiments. Here are some results that I'm showing from Charlie Marcus's group back in 2009. And what they did is they made small devices here, not that small, but 2-micron devices, and they put a top gate over the entire area of the device in an attempt to try to quench some of these strong Coulomb interactions. Now, in the small devices, they weren't able to. They always saw Coulomb-dominated oscillations where you see the lines of constant phase having positive slope. But they also made a very large device, about 20 microns squared, and also had a surface gate over the interior of the interferometer. And here, at least in a subspace of, or in a certain range of filling factor, they were able to see AB oscillations. And you can see the lines of negative slope, constant phase with negative slope in this very large area device. And of course, they increased the capacitance greatly by going to a large area device. But the problem was that if you look at the field scale down below in their plot, it's on the order of half a Tesla. And for the density regime that they're working in, this corresponds to very high filling factor, nu equals 20. And the problem was that while they quenched the Coulomb interaction, they had relatively poor coherence due to the large size of the device. And they could only see AB oscillations at very high filling factor. So the charging energy was quenched by going to a large area device, but the coherence was very poor due to the large path length. So what we need is a better way to screen the Coulomb interaction so we can still work with very small devices that will have small path length and therefore high coherence. And again, these experiments were very illuminating because they did suggest a path forward. What the problem was, we need to keep the device small, but we need to increase the capacitance. So what we decided to do was actually grow the gate, if you will, the screening gates right into the heterostructure. So on the left-hand side, I show you what we call a screening well heterostructure. The central blue region is the 30 nanometer gallium arsenide quantum well, where our two-dimensional electron gas will reside. But in the heterostructure, we added above and below, about 35 nanometers away, two additional two-dimensional electron gases. And as you note in the central panel, we were to show the conduction band profile and the electron density. The density in these ancillary quantum wells, just to the above and below the principal quantum well, is actually quite high. It's higher than the density in the principal quantum well, which in this case is about 1 times 10 to the 11. The upper quantum well has 1.8 times 10 to the 11. And the bottom one has 1.5 times 10 to the 11. And given the high electron density and the proximity to the main quantum well, these ancillary quantum wells are very efficient at screening Coulomb charging effects. Now, this comes at a cost of complexity in device design. We actually have 3 two-dimensional electron gases in parallel, and if we measure transport through this device, we'll see a mess, especially since we want to probe only the transport in the central one, which is the lowest density two-dimensional electron gas. But there is a solution to this problem, and actually it was pioneered by Jim Eisenstein and co-workers back when Jim was studying bilayer systems at Bell Labs. So what we do is build a top and backgated interferometer. We take our sample and thin it down so it's only 50 microns thick, and then we apply gates around the ohmic contacts. Now you can see these gates, this network of gates, that the sort of golden gates that overlay the ohmic arms on the top side, and then the red gates that cover the ohmic gates on the bottom side of the chip. And so if we apply a negative bias, a small negative bias to the top gate, we can deplete the top screening well. And since the sample is thin, we can apply a relatively small, about 150 volts in this case, gate bias on the bottom side, and we can deplete the screening well, the lower screening well, around the ohmic contact. Now transport only takes place through the central quantum well. We've depleted the screening wells on top and the bottom, and this eliminates the parallel conduction. Now, all we've done here is adopted the technique Jim Eisenstein pioneered for bilayer systems. We're applying it to a tri-layer system, and we've shown that it can work with mesoscopic devices, but everything was already worked out for us. And so the important point to keep in mind here, though, is that the interferometer is small, it's very small, and sits on top of the mesa, far away from these depleting gates. So the screening wells are still fully populated and free to screen. From the mesoscopic device perspective, this has no impact on the screening, and so our small interferometer still sees the full effect of the screening wells. So the presence of screening wells enables ABA oscillations, as I'll show you, in small devices, less than a micron in area, and thus they have improved coherence. Equally important, though, I want to emphasize, it's not just the screening, this quenching of the Coulomb charging energy. The screening wells have another benefit in that they promote very sharp confining potentials. We've seen this in simulations, and the evidence is that we have sharp confining potentials. And this is important for 2 reasons. One, the edge state velocity is determined by the electric field at the edge, and so having a sharp confining potential increases the electric field, which increases the edge state velocity. And having a sharp confining potential is good because in soft confining potentials, you can have edge state reconstructions. And we, at least for our preliminary experiments, want to avoid edge state reconstructions and have the simplest edge structure we can possibly have. Okay, so let's move on. So how do we actually demonstrate that we've quenched these Coulomb charging effects? Well, we actually operate our interferometer as a quantum dot. All we do is we pinch down the QPCs so that we're in the tunneling regime, we're at zero magnetic field, and we operate the device as a simple quantum dot. And what we can do is Coulomb blockade spectroscopy on these devices. Again, we're at zero magnetic field. We can apply a finite source drain bias and then apply the side gate voltage, which is essentially what you would call the plunger voltage for a quantum dot, and map out the Coulomb blockade diamonds. Now, on this device with screening wells, we see we can see Coulomb diamonds, but they're fairly small and hard to see actually. If we extract the charging energy from this device, we see that the charging energy is about 17 micro eV that we get from the height of the Coulomb blockade diamonds. Now, if we take exactly the same structure, the same device, and put it on a standard quantum well design where we have no screening wells, we see much different behavior. Here we see the classic behavior of quantum dots where we have large Coulomb diamonds, areas where the conductance is forbidden because we have to overcome the charging energy associated with putting charge onto the quantum dot. And here the charging energy is about 200 micro EV as extracted from these Coulomb diamonds. So by including the screening wells in this heterostructure design, we've actually quenched the charging energy by an order of magnitude. So the screening wells really help quench the charging energy and are going to allow us to operate the device in the Aharonov Bohm regime. Okay, there's again evidence also that the screening wells are important because they give sharper confining potential. Basically, at a qualitative level, you can think of the QPC gate or the defining top gates that define the interferometer as projecting through a mask of the screening wells. And so that the underlying two-dimensional electron gas in a primary quantum well sees the potential of the gates only in a very narrow, sharply defined area. And we can see this by looking at single QPC sweeps at an integer state. So if we go to magnetic field that corresponds to nu equals 1, and we sweep the QPCs, we see quantized conductance at 1 e squared over h, as we expect, where at filling factor nu equals 1, and then a very sharp fall off in the conductance as we pinch the QPC off. If we do the same thing with a more standard heterostructure, we see a more gradual decay of the conductance of the QPC, and we see resonances indicating either some disorder in the QPC in the channel as we're pinching off. But so this change in the behavior of the QPCs, now we're just looking at the QPCs, not the full interferometer, in the quantum Hall regime gives us confidence that we're actually producing a sharp edge profile to back up what's seen in simulations as well. So now let's jump directly to nu equals 1, filling factor nu equals 1 at the boundary between the integer and the fractional quantum Hall regime. And now what I've done is I've taken my same interferometer, but I've opened up the QPCs so that they're only partially reflecting the nu equals 1 edge mode. There we have high transmittance, about 80% transmittance through the QPCs. And what we see is just what we hope to see: negative slope to the lines of constant phase. You can see that the here that the lines of constant phase have negative slope, indicative of being in the Aharonov Bohm regime. And what now we're working at high magnetic field compared to the earlier experiments with the large devices and just a surface gate. Instead of working at 0.5 Tesla, we're working up at 4.5 Tesla in the regime of low filling factor. And so we see Aharonov Bohm interference in a device that's 20 times smaller than was possible with just surface screening gates. Equally important is that the interference is really large amplitude and robust. This device is small, so it's highly coherent. If you look at the scale for the changes in resistance here, it's actually not the conductance, but the resistance, it's many kiloohms. This is really easy to see. You know, anyone could measure this. And what you gather from this is that the device is highly coherent. In fact, if we look at the temperature dependence of the loss of oscillations as we increase the temperature, we see essentially Arrhenius-like behavior, which allows us to extract an energy or temperature scale. And the temperature scale that we extract, which is basically tells us about the coherency of the device, the coherency factor, we extract a temperature scale about 200 millikelvin, which is substantially larger than has been seen before. And so these oscillations survive up to hundreds of millikelvin. And so it's good evidence that we have a highly coherent device. And that's just because we've been able to make the device small. So the path length is small. We're able to make the device small because we've quenched the Coulomb charging effects by using these screening wells. So this is the innovation that we've used to make this transition to being able to go from what are called CD or Coulomb dominated oscillations to working in the more easily understandable and sensitive to, potentially sensitive to fractional statistics, Aharonov Bohm regime. Okay, so now I'm going to jump immediately to the nu equals 1/3 state. We take the same device and just crank up the magnetic field, so we're at around 13 Tesla. And this is from our work about a year ago, our paper that came out in 2019, where we demonstrated, I think for the first time, conclusive evidence that you can be working in the Aharonov Bohm regime in a fractional quantum Hall state. So again, we see lines of constant phase with negative slope. If we analyze the periods, the magnetic field and gate voltage periods of this interference pattern, we arrive with a magnetic field period that's 3 phi naught, 3 times the magnetic flux quantum. And analysis of the gate voltage period allows us to extract the effective charge of the quasiparticles circulating around the interferometer. And we extracted a charge of essentially 0.3 of the bare charge. So we measured multiple devices, and it's always in the vicinity of 0.33. You know, sometimes it's a little bit smaller, sometimes a little bit higher, but always around 1/3 the bare electron charge. So this was nice. It was good that we could see Aharonov Bohm interference in the fractional regime. But one thing that you'll note is in my description early on, I said that we should see if we're really working in the fractional quantum Hall regime and we're introducing quasiparticles, we should see phase slips associated, or glitches, if you will, in this Aharonov Bohm pattern associated with the introduction of quasiparticles. And at least over these relatively small magnetic field regime that we studied in these first devices, you don't see that. You just see pure AB interference. So in a way, you could say this is troubling. Why don't we see it? But in order to understand this, I think we have a fairly good theoretical understanding of this now. We have to compare the relative energy scales. So the energy scales that are relevant are the quasiparticle energy gap. How much energy does it take to introduce a quasiparticle? That's the gap of the fractional quantum Hall effect, which in a sample like this can be quite large. It can be 5 or 6 Kelvin. Whereas the charging energy, as I described earlier from the Coulomb blockade spectroscopy, is quite small. It's about 17 micro eV. So we're actually working in a regime where the system would rather charge up, meaning add charge to the system and stay at fixed filling factor rather than introduce quasiparticles. The quasiparticles take a lot of energy. It's actually easier to charge up the system, at least over some finite range of magnetic field, without the introduction of a quasiparticle and staying at fixed filling. So therefore, if you're at fixed filling, all you're going to see is the Aharonov Bohm phase. So what I've described to you qualitatively, and we outlined in our first paper, was put on firm theoretical footing by Rosenau and Stern in a paper, a PRL from this year. And again, it comes down to a competition between the energy cost to create a quasiparticle and the electrostatic energy cost to add charge to the system but keep filling factor fixed. And they developed a model in which you'll see the 3 phi naught periodicity when the chemical potential is in the gap mid gap between the quasiparticle energy formation. But if you move the magnetic field enough, eventually it becomes energetically favorable to create quasiparticles. And when the chemical potential is in the band of quasiparticles, it actually becomes energetically favorable to do so and not charge up the system anymore. So, so if we go to lower magnetic field, we'll eventually pass a critical field, in which we start introducing quasiparticles. If we go to high magnetic field, we'll go to a regime where we start introducing quasi-holes when the Fermi level or the chemical potential is back in the lower band of the excitation spectrum. So they developed an equation to precisely quantify this region of delta B, where we stay at fixed filling factor. And it's basically the ratio, as I was describing, of the quasiparticle energy gap to a charging energy associated with the charging up of the device, and where this capacitance is the capacitance to the screening layers. And so this defines the region over which we can expect to see just our AB oscillations, and where we might also expect to see a few phase slips associated with quasiparticles that become localized with disorder, pi disorder. So now the next generation of our braiding experiments, we move to even a smaller device and a lower density in the primary quantum well. So we basically reduced the electron density to 7 × 10⁻⁻10 on the primary quantum well. We shrunk the device down even further. And so this has two consequences. One is that going to lower density actually enhances the stability of the device. We can, because we have to apply lower gate voltages, the device is just more stable over broader ranges of applied gate voltages. And because we're at lower density, we can examine the 1/3 state at lower magnetic field. And this enhanced stability allows us to examine the interference over a broad range of magnetic fields around nu = 1/3. So the next step was actually to make the device smaller and lower density. And this was really helped us see features that look consistent with the observation of anyonic braiding. So I'll jump right to the interference pattern at 1/3. And now we've examined it. Now we're at lower magnetic field, but over a broader range of magnetic field. And what you can see is again, the spectra is dominated by these lines of constant phase with negative slope. But here you do see these glitches I talked about that can be associated with localized quasiparticles within the interior of the interferometer. So here I just highlight where these phase slips occur. And we do an analysis of these phase slips by looking at the AB oscillation or evolution in the regions between the phase slips, where we fit the conductance between the jumps to a functional form. Delta G is equal to delta G naught, just the overall amplitude of the oscillations, times this cosine term. The first term in the cosine is nothing but the AB term. There's no free parameters in that. It's just given by the area, the magnetic field we apply, and the quasiparticle charge. And then the additional term, theta naught, which accounts for everything that can't be accounted for by the AB evolution. And so we fix these lines in the AB regimes and extract delta theta. Now to get the phase jumps, theta naught, to get the phase jumps delta theta, we take the difference between the theta naughts on either side of the phase jumps. As you see, we labeled on the top, delta theta over 2 pi is consistently around 1/3. Varies a little bit, minus 0.23, minus 0.28, minus 0.38, minus 0.23, 0.32, but it's always around 0.3. And if we take the average, we get delta theta is minus 2 pi times 0.31 with a standard deviation of 0.04. If we compare that to theory, as I told you earlier, the expected anyonic phase is supposed to be 2 pi over 3 at nu = 1/3. So we take this as experimental evidence that we're actually sensitive to the anyonic phase and the creation of localized quasiparticles within the interior of the interferometer, and that these interference experiments are actually sensitive to not only fractional charge, but fractionalized statistics as well. Now, this we say it's negative, the phase jump is negative. This is consistent with as we increase the magnetic field, we are removing quasiparticles or adding quasi-holes, and so the phase jump across the transition would indeed be negative. Okay, so that's good. That's what we take as experimental evidence, and you can ask me questions about that. There's many ways of analyzing the data. We've gone through the different approaches doing fast Fourier transforms, two-dimensional transforms of the data, and again, we get consistent results that tell us the anyonic phase is approximately minus 2 pi over 3. Now, I want to talk briefly in the time that remains about the reproducibility of these discrete phase jumps. We can do back-to-back scans separated by hours. The discrete phase jumps are always located at nearly the same magnetic field and gate voltage. We raster the gate voltages a lot and over a broad range, and we still see the same thing. It's always consistent with the phase factor of 2 pi over 3. We can explain, I think, the discrete phase jumps within the interferometer. Near the center of the plateau, the chemical potential should be near the center of the energy gap, but of course there is disorder broadening, and there could be a few localized states near the chemical potential. The density of states is small, but there may be a few isolated quasiparticle states due to disorder. And this disorder may explain the uneven spacing of the jumps. They're dictated by the local electrostatics of the quasiparticle energy is modified by the electrostatics, so potential hills or minima that they get trapped in. And this, of course, is due to disorder, and they'll have different locations depending on the specific energetics. And so that can explain why we see uneven space. We wouldn't expect actually to see even spacing of the quasiparticle phase flips. Now, we can also examine this interference behavior over a much broader range of magnetic field than we could before. And here we've shown an expanded view. This is the data before, but over a range of 8.5 Tesla to about 9.5 Tesla. And the data, what we're trying to do here is make closer connection to the predictions of the Rosenau-Stern theory. And so if we look at this behavior where we see essentially a Aharonov-Bohm behavior with lines of constant phase having negative slope, it extends over a region that corresponds to the center of the quantum Hall plateau. And if we measure that just from our measurements, that range is about 450 millitesla. Now, of course, we can measure the excitation gap for this system. We have probes that are probing the bulk on the mesa that probe the bulk of the sample away from the interferometer. And we can measure the gap. And for this particular sample, it's about 5.5 Kelvin. So then we can, of course, form this ratio of the excitation gap to the charging energy that's associated with the capacitance to the screening wells. We know the capacitance. We can just calculate that. And we find that the Rosenau-Stern prediction for where the central region, where we stay in the AB regime, is about 530 millitesla. So we think pretty good correspondence between theory and the experimental measured range of 450 millitesla. Now, at high field and low field, the lines of constant phase flatten out. That's something that we think we understand quantitatively. I don't have time to go into it in this colloquium. It's a fine detail and takes some analysis of the lever arms of the gates, but even there we see quantitative agreement between theory and experiment. So taken together, the phase slips that we see that indicate a phase jump of 2 pi over 3, and this correspondence between a model or extended range of magnetic field, the Rosenau-Stern model, and our data, we take as both as signs of we understand the operation of our interferometer, and it is in fact operating the Aharonov-Bohm regime. This is a detail of enhanced thermal dephasing at low-high magnetic fields. I think I'm running out of time, so I should just move on to the conclusions. What we see is that by incorporating these screening wells into the epilayer structure, we can dramatically reduce the Coulomb charging energy in Fabry-Perot interferometers. This has really is really beneficial for trying to operate in the Aharonov-Bohm regime. We can measure Aharonov-Bohm interference at fractional filling nu equals 1/3. And we think we have pretty strong evidence for direct observation of anyonic braiding. Our experimental extraction of what the change in phase across one of these phase slips is very close to the theory prediction of 2π/3. And with that, I'll conclude and open it up to questions. Thank you very much.
Okay, well, thank you so much for that, Michael. That's a really beautiful result. So let's open up for questions. I think the best thing to do would just be to raise your hand, and then I'll be able to unmute you. Okay, so maybe I'll start. Mike, do you know what the dephasing length is for these fractional edge states at nu equals 1/3?
Yeah, it's interesting. That's experiments that we're doing right now. And so that's part of what we're trying to understand. And it's very interesting. The device does not have to be that large to essentially lose phase coherence. And this explains why a lot of the early experiments weren't able to see interference in the fractional states. If we go to a device that's approximately 1.6 by 1.6 microns, so we've increased the area substantially, but it's still a relatively small device. The amplitude of the oscillations at 1/3 become greatly diminished, and they basically start being washed out. So even going to a device where the perimeter is slightly larger really hurts the coherence of the edge state interference. And so that can give you an approximate scale. We go from a device that's basically half a micron in area to one that's a couple microns squared in area, and we see a strong diminution of the amplitude of the state of the coherence of the oscillation intensity. Now, it's interesting. The states and the integer states are still well formed. We still see very high coherence. So we get very nice interference patterns at nu equals 1. But in the fractional regime, we see a real strong suppression of interference. So it gives you a sense of how big the devices can be and still see fractional interference.
Do you understand at all the dephasing mechanism?
There can be multiple ones, but one that I was going to get to, but I didn't have time to, is that if we move off the center of the plateau, where we don't have many quasiparticles in the interferometer, this temperature scale that we associate with the dephasing changes dramatically. So if we're in the center of the plateau, at the 1/3 plateau, we extract an energy scale or temperature scale about 100 millikelvin. If we go into those flat regions where the interference phase has lost its dependence on magnetic field, we see suppression of interference with temperature, so that the temperature scale is three times smaller, about 30 millikelvin. And what could be going on here is that we actually have something called topological dephasing. There's fluctuations in the number of quasiparticles inside the interferometer. As we move far away in magnetic field, the energy cost to create quasiparticles is very small. It's just a charging energy for those quasiparticles. And quasiparticles can jump in and out of the interferometer, and so that the interfering edge state does not see a fixed quasiparticle number, it sees a fluctuating quasiparticle number. And of course, that will lead to dephasing as well, because you have to have a fixed quasiparticle number to see this anyonic phase. And so it's actually more evidence of the non-local influence of anyonic statistics. The fluctuations in the quasiparticle number lead to rapid thermal dephasing of the interference signal. So that's why we think there's a difference between the integer and the why the fractional states are so much more sensitive to temperature and size and the scale of the interferometer. It's because they can be affected by these quasiparticles popping in and out of the interior of the interferometer.
Okay, anyone else want to chime in?
Looks like Jim has a question.
Jim, yeah.
Hi, Jim.
Can you hear me?
Yeah, I can hear you, Jim. Hi.
Yeah, just wondering, ask an obvious question. Have you looked at 2/5 or 2/3?
Yep, and at 2/3, we can, in our original paper, we did see interference at 2/3. It's not as strong at 1/3, and it's not as easy to interpret. What we are finding and looking, so of course, as you know, 1/3 has the simplest, and a sharp confining potential has the simplest edge structure of any fractional state. What we find is that when we go to fractions that have potentially multiple edge modes and inner edge modes, it becomes very hard to interfere the inner edge modes. They are living in a region where the confining potential can be softer as they move towards the interior of the sample, and we just have a harder time seeing interference. So what we have to do in, say, nu equals 2/3, we have to put the QPCs into stronger backscattering, and if we do that, we can see interference. And again, that was in the original paper. But as you move to these fractions with more complex, possibility for complex edge reconstructions and inner modes, we find in general that it becomes more difficult. So what we're doing now is we're making smaller and smaller devices. You know, I went to the larger limit, but we can make them even smaller than we have right now. And we are seeing stronger interference in devices that are under a micron in area. And so lithographic area is under a micron. So in ones that are basically 0.8 microns by 0.8 microns, 0.8 microns by 0.8 microns lithographically, we do see stronger interference at 2/3, and we're trying to interpret that right now. Inner edge modes are tough.
So nothing yet at 2/5?
We haven't seen anything at 2/5. No, we just recently tried in one of these large devices. We have a larger device in right now, and what we saw was that in the large device, there's reduction in amplitude at 1/3. We can still see interference, but it's not as strong as the data I showed you. And then we looked specifically at 2/5 and couldn't see anything.
Thank you very much.
Yep, that's where we stand.
Okay, any other questions? I have one more, actually, hopefully quick question. To follow up on your response to my first question, Mike, have you looked for telegraph noise at nu equals 1/3? You know, I mean, to put context, if you think you're entering a regime where you have potentially rapid generation of bulk quasiparticles and then removal of bulk quasiparticles, that might manifest as phase-ups coming in and out as a function of time in the conductance.
Yeah, I think that's probably happening too fast on our measurement time scale. The short answer is no. We've been trying to make the devices as stable as possible, and they tend to be fairly stable. But we have not specifically looked for telegraph noise, and maybe something worth doing. I have to consider the timescales, where we might have to look, but no, we haven't.
It seems like might have a window since you where you see the nice anyonic braiding phase. You see that the device is very stable. And by maybe just changing the magnetic field or gate voltage, moving deeper into the
yeah, that's a good point, and I think we could find some intermediate regime. Now, in the center of the plateau, we think that there's just a few quasiparticle states that are localized by disorder, and that we can't have a proliferation of quasiparticles because they're still protected by the gap. As we move the magnetic field, of course, that's the energy scale changes, and then we get into a regime where the chemical potential is in the band of quasiparticles, and that's just the charging energy. So that's a very small energy scale. So that can happen very rapidly. But as you say, there may be some regime where we've tuned out of the central region where we have stabilized quasiparticles, small number of well-stabilized quasiparticles, to a regime where we could see some telegraph noise. That's actually a good thing to think about. You should try it. Thanks.
Yeah, sure. Okay, so it looks like there's no more questions.
Oh, no more questions? No.
Not that I see. Well, Mike, thank you again so much for this wonderful talk and sharing these really exciting results with us. Look forward to learning more in the future.
Well, thank you for inviting me. I appreciate it.
All right, thanks, Mike.
Okay, thanks, everyone.
Bye, everyone.